good afternoon.
First of all, I want to thank you for staying here and listening to my words. So this is Elie Merhej. I'm an M2 student and doing my internship in quantum computation. More precisely, I'm working on contextuality of magic states. So first of all, we'll start with a summary. First of all, we're going to give an introduction to quantum contextuality. But before doing that, we're going to introduce ourselves to quantum advantage. Then we're going to talk the definition of quantum advantage will be followed by the sources behind this quantum advantage or speed up. Then we're going to introduce quantum contextuality and why we care about such quantum effect. Then we're going to go a little bit more deeply and talk about contextuality of magic states, and we're going to talk about the two great bills, qubit case and the qubit case, knowing that the qubit case is a d-dimensional quantum mechanical bit, whereas for the qubit case, it's for the dimension d equals to 2. Then we're going to present our main work, hardness for classical simulability. We're going to talk about universality and anti-consumption. So, first of all, what is quantum computational advantage? Any integer n that I want. So this source factoring algorithm, this quantum algorithm, it runs in polynomial time, which is almost exponentially better than the most classical algorithm, which does the job of factorizing this algorithm. So if you can see here, for example, let's take an example. For a number of digits, capital N equals 600, we'll observe that a conventional computer will do the job with 10 to the power 14 computational steps. So it's going to factorize the number with 10 to the power 14, whereas a quantum computer will do this job with approximately 10 to the power 8 computational steps. That's the marginal and the drastic difference between quantum computer and conventional computer when it comes to speed up quantum computations. So, now, okay, quantum advantage, it's something that's really great. We really care about quantum advantage, but thinking about its underlying sources, it's really even greater than that. So, one raises the fundamental questions. What are the unique resources that belong to the quantum world which enable us to do this quantum speed up? Many attempts, historically, many attempts, including quantum superposition and quantum entanglement, and the necessity, more precisely, the necessity of large amount of entanglement were proposed to solve such dilemma and question. Unfortunately, none of these quantum effects, they could solve such dilemma. In fact, the necessity of large entanglement, it's not the real source for quantum contextuality. For example, if we take the pure state, there exists some pure states which are highly entangled, yet they do not offer universal quantum computing. So we need to take care about one thing that's very important. What I'm trying to say here is the following: quantum entanglement, it is the source for quantum contextuality, but one, quantum entanglement, it's not the unique resource for universal quantum computations or for quantum advantage. And two, which is most importantly, the equation which tells me that high amount of entanglement will allow me to do quantum speed up, this equation, it does not exist. So I do not need high entanglement in order to have quantum speed up. That's very important. But yet quantum entanglement, it is a unique resource, yet highly entangled state, they're not useful for quantum speed up. For example, there exists some, for example, the states which are sampled from Haar measurements, they are highly entangled, yet they do not offer universal quantum speed up. So this is where we need to think about quantum contextuality, and this is where quantum contextuality gets into the puzzle. So what is quantum contextuality? Before defining quantum contextuality, we need to mention that quantum contextuality lies at the foundational concept of quantum mechanics. It is a purely quantum effect. There is no known classical contextuality. This classical contextuality, it does not exist. It's purely quantum. And as a definition, for quantum contextuality, if the outcomes of any measurement is dependent upon what other measurements are done with the same set of measurements. For example, if we see this example, this very basic example, if I have an observable, a quantum observable A, and my job is to measure this quantum observable A, I need to care about the environment of this quantum observable A. And what I mean by that, this environment in mathematical physics, it's the observable B. So for example, if I'm measuring A with the environment, this quantum observable B, I will obtain the outcome result X. Whereas if I want to measure, or if I wish to measure the quantum observable A with a new environment, which is C, the quantum observable C, I will obtain an outcome result Y. And here, for the sake of simplicity, I am saying outcome result X and outcome result Y, but in fact, it's an output distribution. I have a probability of obtaining such result and a probability of obtaining such result, but for the sake of simplicity, I'm writing outcome result X and outcome results Y. So the main idea behind this is to tell that the environment, it's affecting the measurement. So here, when I'm measuring with a commuting observable B, I'm obtaining result X, whereas here I'm working with the outcome result Y. Here's where contextuality comes into the puzzle. Right. So why do we care about quantum contextuality? First of all, according to Bell, Cauchy, and Specker theorem, there is non-contextual hidden variable theories. They are not compatible with quantum mechanics. At first, contextual hidden variable theories, so first of all, contextual hidden variable theories, they try to explain or predict quantum phenomena using something that we call pre-existing value or element of reality. So these, let's say, mathematicians, they used to say that, okay, I have this quantum system, I can predict the outcome result of this quantum system if I have some variables of element of reality that we call hidden variables. Fortunately, Bell, Specker, and Cauchy theorem, they proved that's the impossibility of doing this. So hidden variable model, it is incompatible with quantum mechanics, and quantum mechanics is contextual. That's why we care about quantum contextual. That's why we care about contextuality, because quantum mechanics, it is contextual from one point, and from the other point, it is believed that quantum contextuality lies at the heart of quantum computations. So now contextuality of magic states, what we are working on. So there exists two big pillars in contextuality of magic states, the qubit case and the qubit case. Starting with the qubit case, qubit magic states are a particular type of quantum states, which, first of all, they lie outside the simulable set of polytope. And what's the simulable set of polytope? The simulable set of polytope, it contains the simulable states. And what are the simulable states? They are the states which can be efficiently classically, so this simulable polytope, it contains the simulable states which can be efficiently classically computed via classical algorithms. Yes, so qubit magic state, there are states which lie outside this simulable polytope, so they're not simulable states. Plus, they possess state-dependent contextuality property. So quantum contextuality is a necessary resource for the qubit magic states to attain quantum speedup. On the other hand, if we want to talk about the qubit case, unlike the qubit case, it possesses different types of contextuality, plus it lies outside the set which contains the stabilizer states. Here, note that for the qubit case, and if we want to talk about geometrical polytope, the stabilizer polytope, it is equal to the simulable polytopes for p equals 2 for the case of qubits. That's why qubit magic state, they lie outside the stabilizer polytope. That's it. But unfortunately, characterizing contextuality for qubits is a bit more tricky due to the presence of a state-independent contextuality. So in that case, fortunately, that's not my work. I'm working on the qubit case. But for the qubit case, this state-independent contextuality makes life, it's even trickier. So that's why that's not my work. I'm not working with this. But to generalize, that's how for the qubit case. Right. So finally, what we are trying to prove, hardness to sample classically. So first of all, for the article of Howard 2014, which is Contextuality Supplies the Magic, Howard, he could prove that magic states, they're contextual. How did he do that? He proved at first that a qubit magic state, they exist outside the simulable polytope, so it's not a simulable state. And he do that by violating the non-contextuality inequality. So QDIT magic states, they are contextual. Now, when QDIT magic states, which are contextual, they are promoted in stabilizer circuits, this is when we can attain universality, hence universal quantum computing. So that's it. Now what we want to do is the following. We need what are the upcoming results that we are rating. So first of all, we need to design a QDIT magic state. We need to then we need to perform Weil-Heisenberg measurements. So we need to perform some architecture based on Weil-Heisenberg measurements and not Hadamar's, neither C0s or the phase shift due to the d-dimensional quantum bit because we're working with QDITs. So performing Weil-Heisenberg measurements, we're waiting for an output distribution, and this output distribution, we want it to be anti-concentrated. If we obtain anti-concentration for such distribution, this is when we can obtain hardness. This is when we can tell that, classically speaking, we can obtain hardness for classical sampling. Yes. And then for the future plans, what we're trying to tell, as I have said moments ago, that QDIT magic state, they exist outside the simulable polytope, but actually there are few magic states, there are few states which exist outside the simulable polytope. They're not the full states. There exist other states outside the simulable polytope. So what we want to do is we want to prove that these states, they are equivalent to magic state, and therefore they are contextual, and they're contextual. And that's it. Thank you. Any question? Yes.
Very like time or frequency you're working with. Can you tell us about it's changing in time or in frequency?
Here we're not working with time nor the frequency. Here we're just working with universality and anti-concentration. Time doesn't exist here in what we're doing. I think you're talking about Shor's factoring algorithm, the exponential speed up. You're talking here, I think.
No. I'm talking about when you pick your polytope.
Yes.
You don't have any time parameter?
No, it's not about time. It's about you designing your QDIT magic state, and you need to prove that it's magic state. What does it mean? You need to prove that it lies outside the simulable polytope. That's what you should do. There has nothing to do with time. You don't need to prove that. So you have your rho n. If you're preparing n copies, let's say, you have your rho n, tensor product n, and you're proving that it lies outside this simulable polytope. That's how you should do in order to prove contextuality. There has nothing to do with time, actually. Yes.
So for the anti-concentration,
yes,
is this also based on like QDIT versions of T-design? Is that the idea a bit?
Unfortunately, what we're trying to talk for the moment is we know that, or we believe that you can attain universality and you can attain hardness without the concept of anti-concentration. But unfortunately, now mathematically speaking, we need to induce anti-concentration in our results in order for us to prove hardness. So yeah, until now we need anti-concentration for hardness. Okay. We believe so, at least.
All right, thanks.
Thank you. Thank you. Thank you very much.